This question is from GATE 2015 Mechanical Engineering paper, set 2, question number 37. A hollow shaft of 1 meter length is designed to transmit a power of 30 kilowatt at 700 rpm. The maximum permissible angle of twist in the shaft is 1 degree. The inner diameter of the shaft is 0.7 times the outer diameter. The modulus of rigidity is 80 gigapascal. Outside diameter in millimeters of the shaft is dash. Let's write down the given information. We have length of the shaft is given to be 1 meter. Power transmitted by the shaft is 30 kilowatt. This can be converted to watt by multiplying with 1000. So we have 30,000 watt or 3 into 10 to the power 4 watt. Speed of the shaft is given in terms of, and it is 700 rpm. Maximum permissible angle of twist, theta, is given to be 1 degree. This will have to be used in the unit radians. So we'll convert this into radian. This will be pi by 180 radians. Inner diameter of the shaft, di, let that be di, is given equal to 0.7 times the outer diameter, let that be do. Modulus of rigidity G is also given 80 gigapascal. And gigapascal can be converted to SI unit pascal by multiplying it with 10 to the power 9. So we'll get the unit in pascal. Let's find out the outside diameter now. So the first relation which we'll start with is the relation of power with torque and speed. Power developed by the shaft is equal to torque applied to it into its angular velocity that it gains because of this torque. This angular velocity can be found out using speed n, which is nothing but power can be written as T into angular velocity omega is written as 2 pi n by 60. By rearranging this, we have P and N, so we can find out T here. Therefore, T will be equal to 60 by 2, that means 30. 30 into power is 30,000 watts, so we can write 3 into 10 to the power 4 divided by pi into speed is 700. This when calculated using digital calculator gives 409.255 Newton. Now we have the torque with us. We will use the pure torsion equation T by J, where J is the polar mass moment of inertia, is equal to G theta by L. As given, G is the shear modulus, modulus of rigidity, theta is the angle of twist, and L is the length of the shaft. So we know all of these four quantities. The thing that we don't know is the polar mass moment of inertia, G, because we don't know the diameters. So we can find J from here. Hence, by rearranging, J will be equal to T into L by G into theta. Let's substitute. T we found out here. It is 409.255 into length of the shaft is given to be 1 meter divided by G we have converted here 80 into 10 to the power 9. And theta was given in degree, we have it here in radian. It is into pi, 180 taken to the numerator. So this becomes into 180. This when calculated, we get J as 2.93 into 10 to the power minus 7 meter raised to 4. Because everything was in SI units, we got J in terms of meter raised to 4. Let's convert this to millimeters raised to 4. This will be equal to 2.93 into 10 to the power minus 7 into 10 to the power 3 raised to 4. Right? 10 cube raised to 4, which is 12. 10 cube 12. 12 minus 7 is 5. So this is nothing but 2.93 into 10 to the power 5 millimeters raised to 4. We know that polar mass moment of inertia J can be written in terms of diameter. Polar mass moment of inertia of a hollow cross section is given as pi by 32 into d naught raised to 4 or d outer raised to 4 minus d inner raised to 4. And that we found out here. So we can equate it to 2.93 into 10 to the power 5. Let's substitute. The relation between di and do is given. We can substitute as this di is equal to 0.7 times do. So we will get pi by 32 into do raised to 4 as it is minus 0.7 times do raised to 4. So we can separate it out. 0.7 raised to 4 into do raised to 4 is equal to 2.93 into 10 to the power 5. Let's rearrange this to get do raised to 4. So we'll get here do raised to 4 taken common is equal to 2.93 into 10 to the power 5 into 32 divided by. The numerator terms on LHS were pi into. After taking do raised to 4 common, we had in the bracket 1 minus 0.7 raised to 4. This will give us 3.927 into 10 to the power 6, and the unit should be meter raised to 4 itself because this is do raised to 4. So we can find out the outer diameter from here. The outer diameter do is equal to this value 3.927 into 10 to the power 6 to the power 1 by 4, which is equal to, by using the digital calculator, we calculate this as 44.518 millimeters of diameter, because we have already converted here the value of J in millimeter raised to 4. That is why we got the diameter directly in millimeters. Let's substitute this in the answer. So outside diameter in millimeters of the shaft is 44.518 millimeters. To learn more about torsion on shafts, you can refer to the NPTEL video Lecture 18, Torsion 1 from the course lecture series on Strength of Materials by Professor S.K. Bhattacharya. He is from Department of Civil Engineering, IIT Kharagpur. I hope this solution will help you clear your doubt. Thank you.